So, guys, good evening and welcome back again to your Unacademy NEET English channel. I hope all of you are doing great, having a good time. So, my dear students, quickly give me some green signal from the chats so that I'll get to know I'm perfectly audible and visible to every one of you. Quickly let me know in the chats with the thumbs ups. Welcome back, guys. Welcome back. Welcome back. Welcome back. So, what's up? How you all guys doing? All great? Yeah? All good? Good evening, all. Good evening. Good evening. Perfect. So I think I'm perfectly audible and visible to everyone. Yeah? That's wonderful. So, my dear students, as you all must be knowing, today it's going to be a detailed marathon, a one-shot marathon of the chapter Chemical Equilibrium. One of the most interesting chapters and one of the most difficult chapters as per students' perspective is concerned. Yeah? But my dear students, again, what I keep on doing always, I'll be starting this chapter exactly from the basics. I'll be starting it from the scratch so that you can get all the concepts in detail and you can solve all the problem patterns of the chapter Chemical Equilibrium, right? And I would say 90% of the problem patterns from the chapter I'll be doing here only in the today's session. And today's session will be approximately some 4 to 5 hours, right? And I believe 5 hours should be enough to complete this particular chapter from exact scratch, from exact basics. So before starting the session, you need to tell me in the chats if all of you are again super duper excited about this particular session. Quickly, my dear students, so that we can start the session directly without wasting a lot of your time. Quickly, let me know in the chats if all of you are again super duper excited about this particular session. Perfect, guys. Wonderful. Wonderful, wonderful. Ashish, this is the English channel. I'm not supposed to talk in Hindi. Okay? We have got a lot of Hindi channels of Unacademy too, right? You can check them up. You are going to love them too. Yeah? And anyways, I'm not going to speak some French English or whatever, American English. It's going to be a normal English, which a common man can understand too. Yeah? Perfect. So let's get going then. Let's get started. So dear students, before starting this particular session, the ones who are new to the channel, the ones who do not know me, a quick introduction about me. My name is Wassim Bhat and I'm your chemistry educator on this particular Unacademy NEET English channel, right? And this is all about me. You can check it out afterwards when you get the time. Yeah. And at the same time, the ones who have not liked this particular session, I would want every one of you to like this video, share this particular video with everyone, whosoever cannot afford the paid batches, whosoever cannot afford the quality education. Let them know that this is the channel which does not compromise on the content, right? Whatever we teach on the paid batches, same is the content which we give here on YouTube as well, right? So for that purpose, you need to like the video, share the video with everyone, right? Let all your friends get benefited out of these sessions. And at the same time, if you have not subscribed to the channel yet, I would want every one of you to subscribe to the channel so that you remain updated about all the sessions which we take live on this Unacademy NEET English channel. Yeah? Perfect? All right, people. Just give me a second. Just give me a second. All right. So let's get going then. Let's get started with the chapter. Again, I'm telling you, I'll be starting exactly from the basics. And whatever points I'll be noting down on the screen, I would want all of you to take a note of every single thing because every single thing is equally important, my dear students. Right? And we'll be exactly starting from the basics. So first of all, if I talk about equilibrium, how do we define equilibrium basically? My dear students, as per thermodynamics point of view is concerned, as per thermodynamics point of view is concerned. Equilibrium is defined as that state of the system. Equilibrium is defined as that state of the system at which entropy attains its maximum value and Gibbs free energy attains its minimum value. This is the definition of equilibrium as per thermodynamics point of view. Equilibrium is nothing, it is just the state of the system. It is one of the state of the system at which entropy of the system attains the maximum value, Gibbs free energy attains the minimum value. And you must be knowing now, as per thermodynamics is concerned, whenever entropy attains its maximum value and Gibbs free energy attains its minimum value, that state of the system is considered to be the most stable state of the system. So what is equilibrium? What is equilibrium? I would say equilibrium is basically a state of the system at which entropy of the system becomes maximum, Gibbs free energy of the system becomes minimum, and as far as thermodynamics is concerned, that state of the system where entropy is maximum, Gibbs free energy is minimum, that is considered to be the most stable state of the system. That is why your equilibrium, that is considered to be the most stable state, right? This is the general definition as per thermodynamics is concerned, right? Perfect. This is the general definition as far as the thermodynamics point of view is concerned. Now let's go into the details of this equilibrium and let's get to know one by one what this equilibrium is all about. Yeah. Now, my dear students, try to understand what exactly I'm going to say. Try to understand what exactly I am going to say. Okay? Try to understand everything. Now I'm going to start the chapter basically. All right. So first thing, what exactly we are going to do? We are going to talk about the equilibrium as per chemical reactions are concerned. We are going to discuss the equilibrium of chemical reactions. Okay? The first point which I would want every one of you to remember. Equilibrium in chemical reactions, how do we define it? I would say it is the state of the system. It is the state of the system. It is the state of the system at which all the measurable properties, all the measurable properties of the system like moles, concentration, pressure, temperature, color, etc. attains a fixed value. Or you can say becomes constant. What this particular point exactly means? My dear students, it's again very simple. See, first of all, when do we say that equilibrium has attained in a chemical reaction? When do we say that equilibrium has attained in a chemical reaction? What is equilibrium first of all? It is the state of the system. So when do we say that equilibrium state has attained in a chemical reaction? My dear students, when all the measurable properties like moles, like pressure, like concentration, when they become fixed, what does that mean? You will see one particular point in a chemical reaction. You will see one particular stage in a chemical reaction at which all the moles of reactants and products, they will become fixed. They won't change at all. You will see a particular state in a chemical reaction at which the concentration of all the reactants and products, they will become fixed. They won't change at all. Right? You will see a particular state in a chemical reaction at which the pressure of reactants and products, it becomes fixed, it becomes constant, it does not change at all. That particular state in a chemical reaction, at which moles of reactants and products, they become fixed, they become constant. Concentration of reactants and products, they become constant. Pressure of reactants products, they become constant. That particular state is something we call as equilibrium state in a chemical reaction. Right? This is something which we are going to study in detail in some time, right? So first of all, I would want you guys to remember this particular statement. It's very, very, very important, right? The detailed explanation of this particular statement you will get in some time. Just you take a note of things first. So what is equilibrium in a reaction? It is that state in a chemical reaction at which the moles of reactants and products, they become fixed. They do not change at all. Concentration reactant products, it becomes fixed. It becomes constant. It does not change at all. Pressure of reactants products, it becomes fixed. It does not change at all. And that particular state is something which I'll be calling as equilibrium state in a chemical reaction. Point number one. My dear students, point number two. Equilibrium is always attained in reversible reactions. Equilibrium is attained always in a reversible reaction. Now the point is, what are reversible reactions? Just the quick idea. For example, I'm going to denote a reaction like this. A gives B and B gives A. A gives B, B gives A. That particular reaction which can proceed in both the directions, forward as well as backward. That particular reaction which can proceed in both the directions, forward as well as backward. That's something which you call as a reversible reaction. And equilibrium is always attained only in case of reversible reactions. In irreversible reactions, equilibrium cannot be attained, right? So equilibrium is what? It's the state of the system, right? It's the state basically, which is attained only in reversible reactions. And the reversible reactions are the ones which proceed in both the directions, forward as well as backward. This is second point. My dear students, the third point. The third point. Understand properly what exactly I'm trying to say. I'm writing over here as the reaction proceeds. As the reaction proceeds. As the reaction proceeds. The concentration of reactants, it decreases. And the concentration of products, it increases. As the reaction proceeds, the concentration of reactant decreases with time. And the concentration of products, it increases with time. Now you must be thinking, what is meant by the term concentration? Concentration is nothing. It is represented by square brackets, and concentration is defined as number of moles per unit volume of the system in liters. What does it mean? Try to understand what I'm going to say. For example, I have got a reaction like this. A gives B. Let's assume this is a reaction. Okay. Now this particular reaction has to take place basically. This reaction has to happen. I'm assuming that this particular reaction will be taking place in a container whose volume is V liters, right? So what is V liters? It is the volume of the container in which this particular reaction has to proceed, in which this particular reaction has to occur, right? Now guys, if I say time t is equal to 0, time t is equal to 0 means the reaction has not started yet. Reaction has not started yet. What does that mean? That means the reactant has not started getting converted into product. The reactant has not started getting converted into the product. I'm assuming that at time t is equal to 0, I have got 10 moles of reactant with me. Since the reaction has not started, so product formation at this particular point will be 0. Now, my dear students, what is going to happen? When the reaction will proceed, what is going to happen? When the reaction proceeds, I'll say the number of moles of reactants will keep on decreasing with time. And number of moles of products will keep on increasing with time, right? So number of moles of reactants will keep on decreasing with time, and number of moles of products will keep on increasing with time. So what I got to know? I got to know with time, when the reaction starts, moles of reactants keep on decreasing, and moles of products in a reaction, it keeps on increasing, right? Concentration is number of moles per unit volume. If I write concentration of reactant, what does that mean? That means number of moles of reactant divided by volume of the system in liters. If I write concentration of products, which means number of moles of products divided by volume of system in liters. Now you are going to tell me one thing. When the reaction proceeds, are the moles of reactant increasing or decreasing? When the reaction starts, the number of moles of reactants, they decrease with time. And if number of moles of reactant decrease with time, that means concentration of reactants, it decreases with time. Similarly, number of moles of products in a reaction, it increases with time. Therefore, concentration of products, it again increases with time. So my dear students, this is a very important statement and simple, basic at the same time. When the reaction starts, moles of reactant decrease with time. Concentration of reactants decrease with time. Moles of products increases with time. Concentration of products increases with time as well. Right? Let me note down this particular statement in terms of graph. Let me note down this particular statement in terms of graph. Have a look exactly what I'm going to say. My dear students, I'm going to plot a graph. The graph is between concentration versus time. The graph is between concentration versus time. Right? So first of all, if I need to plot a graph between concentration versus time or reactants, how exactly we are going to do that? My dear students, we know with time, concentration of reactants, it decreases with time, right? So this is the graph which is valid for what? It is the graph which is valid for the reactant. Similarly, I want you guys to plot a graph again between concentration versus time, but for products. And you know, for products, with time, the concentration of product increase with time, right? The concentration of product increase with time. Yeah. At time t is equal to 0, number of moles of product are 0. So when the reaction starts with time, the moles of product increases. That means the concentration of product increase as well. So this is how your concentration of products increase with time. So first of all, I would want you guys to remember these two basic graphs. With time, the concentration of reactant keeps on decreasing. With time, the concentration of products keeps on increasing. Right? One basic thing. Now guys, try to understand one more important point. First of all, there is one law which we have to discuss here in this chapter only after some time. But I would want its basic thing over here as well. After some time, I'm going to discuss that law in detail, but I would want one of its points. And what is that point? There is a law called as law of mass action. As far as law of mass action is concerned, we can say rate of reaction, it is directly proportional to concentration of reactants. It is basically active mass of reactants, but since we have not discussed active mass yet, so I'm directly writing rate of reaction is directly proportional to active mass of reactants or concentration of reactants. What does it mean? Why do I need this particular term? Try to understand what I'm going to say. For example, imagine that you have got a reaction like this. A gives B. So first of all, it is a reversible reaction. This reaction can proceed in both the directions, forward as well as backward. Right? It can proceed in both the directions. Now, my dear students, try to understand one simple thing. Let's assume that at time t is equal to 0. Let's assume that, or let's do one thing. Tell me one thing. Whether it's actually a single reaction or these are actually the two reactions. If you ask me, I would say these are actually the two reactions. The first reaction is the forward reaction in which A gives B. The second reaction is the backward reaction in which B gives A. So this is my forward reaction and this has to be my backward reaction. Perfect. My dear students, for the forward reaction, the reactant is A. And for the backward reaction, the reactant is B. Right? So, as per law of mass action is concerned, I would say rate of forward reaction is directly proportional to concentration of reactant. Which is the reactant in the forward reaction? It's A. Right? Similarly, I can say as per law of mass action, rate of backward reaction is directly proportional to concentration of this B, which is the reactant of the backward reaction. Perfect. I can say something like this. Rate of forward reaction is directly proportional to concentration of reactant here. Rate of backward reaction is directly proportional to concentration of reactant here. And B is the reactant in this particular case. Perfect. Now you tell me one thing. Few minutes back I told you. If you talk about this particular reaction, in this general reaction, this A is your reactant, B is your product. When the reaction starts, the concentration of this A will start to decrease. And when the reaction starts, the concentration of this B, it will start to increase. Right? And my dear students, if the concentration of A decreases with time, that means the rate of forward reaction, it decreases with time. If the concentration of B increases with time, that means the rate of backward reaction increases with time. So can I say something like this? When the reaction starts, rate of forward reaction, the rate with which forward reaction moves, it decreases with time, and rate of backward reaction increases with time. So can I say a stage will come at which rate of forward and backward reaction becomes equal? And that particular stage in a chemical reaction at which rate of forward and rate of backward reaction becomes equal, you call that particular stage in a chemical reaction as the equilibrium stage. So I would say when rate of forward and backward reaction becomes equal, we would say at this particular point of time, we can say equilibrium is established in the reaction. We can say equilibrium is established in the reaction. So in the reaction, a state has reached at which the system would have attained its maximum entropy and Gibbs free energy of the system would have attained its minimum value. So this particular state of the system will be considered as the most stable state of the system, right? That is the reason why every reversible reaction wants to attain equilibrium as soon as possible, because equilibrium is the most stable state of the system. And every reversible reaction would want to go towards stability as soon as possible, right? Let me know once in the chats if this particular point is clear to everyone. Quickly. So equilibrium is that state of the system at which rate of forward and rate of backward reaction becomes equal. Yeah? Quickly, my dear students. If you would want to do one simple thing, if you would want to represent all these things graphically, you can do that as well. I told you at equilibrium, rate of forward and rate of backward reaction becomes equal, right? Rate of forward and rate of backward reaction becomes equal. Why is that? Because with time, when the reaction starts, rate of forward reaction decreases with time and rate of backward reaction that increases with time. So if this particular statement you will have to represent with the help of graph, you can do that as well with the help of graph. If you want to plot a graph between rate of reaction versus time, rate of reaction versus time, you know, as I told you a few minutes back, rate of forward reaction that decrease with time, right? That decrease with time. And I can say rate of backward reaction, it increases with time. And this is the point. This is the point after which rate of forward and rate of backward reaction becomes equal. So I would say this point represents the time when we say equilibrium has established in the reaction. So after this particular point, rate of forward and rate of backward reaction, it has become equal. So I would say at this particular point of time, equilibrium has attained in the reaction. I hope this particular point is clear to everyone, right? This particular graph, it is the rate of forward reaction. And this one, it is the rate of backward reaction. Rate of forward reaction decreases with time and rate of backward reaction increases with time. Therefore, a stage will come when rate of forward and backward reaction becomes equal, and that particular state in the system is what we call as equilibrium state. It's what I call as equilibrium state, right? Isn't it simple, my dear students? Isn't it simple? Isn't it simple? Say yes or no in the chat quickly. Yeah? I hope this particular statement is clear, right? At the same time, my dear students, let me tell you one more thing about equilibrium. I would say equilibrium is always dynamic in nature. Equilibrium is always what? It's always dynamic in nature. That means when equilibrium is attained in the reaction never stops because the rate of forward and backward reaction is equal. The rate with which forward reaction moves, with the similar rate, backward reaction also moves. So it keeps on going. The rate with which forward reaction goes, in the similar way, backward reaction also goes. The rate with which forward reaction moves, in the similar way, rate of backward reaction is the same. Perfect. So the reaction keeps on going continuously. Forward and backward reaction, they keeps on taking place at equal rates. That's why once equilibrium is established in the reaction never stops. It's always dynamic. Forward, backward, continuously it will keep on moving. Yeah. At the same time, one more important point about equilibrium. What is that going to be? Try to understand. Try to understand. Any reaction, any reversible reaction involving gaseous reactant or product. involving gaseous reactant or product can attain equilibrium only in a closed container, only in a closed vessel, closed container. Why is that? Try to understand this particular point as well. Try to understand this particular point as well. For example, my dear students, I'm taking one container. This is, for example, a container which is open on one side. The container is open on one side. Now, for example, over here, we have got calcium carbonate solid, right? You know, when calcium carbonate is heated, it gets converted into calcium oxide, and with this, you'll be getting carbon dioxide gas. Perfect. So, my dear students, if the vessel is open on one side, I have introduced calcium carbonate in the container, right? After introducing calcium carbonate in the container, I'm going to heat it up. When I'll heat it up, it will start getting converted into calcium oxide. And with calcium oxide, you'll be getting carbon dioxide gas as well. So a gas is getting produced here. When calcium carbonate is heated, gas is getting produced. Where would that gas go? Since the container is open on one side, whatever carbon dioxide is produced, that will come out of the container. And if carbon dioxide will come out of the container, there will be no carbon dioxide left in the container. If there is no carbon dioxide left in the container, is it possible for the backward reaction to happen? The backward reaction won't happen. And if the backward reaction won't happen, that means the reaction cannot be reversible. And if the reaction won't be reversible, what will happen? Equilibrium cannot be established in the reaction. Yeah? So for any reaction which involves minimum one gaseous reactant or product, equilibrium will be established only in that particular reaction in a closed container. Yeah? I hope this is super clear to everyone. Say yes or no in the chats quickly. Say yes or no in the chats quickly. Say yes or no in the chats quickly. Try to understand one more important point, which is the most important point related to equilibrium, right? Yeah, which is the most important point related to equilibrium. See guys, this is the most important point. What is that? I would say at equilibrium, what happens? Number of moles of reactant and number of moles of product, they become constant. They do not change at all. Concentration of reactant and concentration of product, they also attain a fixed value. That means they become constant. Partial pressure of reactant and partial pressure of product. Partial pressure of reactant and product, it also becomes fixed. It also becomes constant. Now what it means exactly, what these things mean. Try to understand these three important points, which are very, very, very important. So at equilibrium, the moles of reactant and products, they do not change after that. Once equilibrium is established in the reaction, after that, the moles of reactants and products won't change. The concentration of reactant product, it won't change. The partial pressure of reactant and product, it won't change. Why is that? Let's try to understand. For example, I've got a reaction A in equilibrium with B. This is a reaction, a reversible reaction. Let's say, for example, at time t is equal to 0, I have got 10 moles of reactant with me. So that means there will be 0 moles of product present in the container in which this reaction has to happen. I'm assuming that the container in which reaction has to take place, volume of that container is, for example, 1 liter. Just to make you understand. Right? Now, my dear students, try to understand one thing. At time t is equal to 0, we have got 10 moles of reactant. We have got 0 moles of products in the container in which reaction has to take place. Let's assume that when the reaction is, for example, 20% completed, equilibrium is established in the reaction. When the reaction is 20% completed, let's assume that equilibrium is established in the reaction. Now you tell me one thing. What does this 20% completion mean? It means that 20% of the reactant would have got converted into the product, right? You tell me, how many moles of reactant we had? We had 10 moles of reactant. Out of 10 moles, 20% of 10. 20% of 10 means 2 moles, right? So out of 10 moles of reactants, I would say 2 moles of reactant would have got converted into products. Now you tell me, if out of 10 moles of reactants, if 2 moles of reactant got converted into product, let's say I'll be left with 8 moles of reactant at equilibrium. Similarly, how many moles of product would have got formed? I would say 2 moles of product would have got formed. Right? I would say 2 moles of product would have got formed. Perfect. So my dear students, try to understand one more important thing. It's important. At time t is equal to 0, I'm assuming that we have got 10 moles of reactant, 0 moles of product. I'm assuming when 20% of reaction gets completed, equilibrium is established in the reaction. 20% completion means that 20% of reactant has got converted into products. So initially I had 10 moles of reactant. 20% of 10 moles has got converted into product. 20% of 10 is 2, right? So out of 10 moles, 2 moles of reactant has got converted into product. So I'll be left with 8 moles of reactant, and I would say 2 moles of product would have got formed as well. Now what has established in the reaction? Equilibrium. If equilibrium is established in the reaction, I would say now the rate of forward and backward reaction would have got equal. What does that mean? That means if 1 mole of reactant will start getting converted into product, at the same time 1 mole of product will come into reactant side. If 1 mole of reactant gets converted into product, at the same time 1 mole of product will get converted into reactant. What does that mean? That means the number of moles of reactant and product will not change now. The number of moles of reactant and product, they have become constant. They are not going to change now. That's what I told you. When equilibrium is established in the reaction, the moles of reactant and product are not going to change. Right? Now, my dear students, what is concentration? Concentration is number of moles divided by volume, right? So if I ask you at equilibrium, how many moles of A we have? 8. So if I ask you at equilibrium, what will be the concentration of A? At equilibrium, what will be the concentration of A? You will say moles of A divided by volume. Moles of A at equilibrium is 8, volume is 1. So the concentration of reactant at equilibrium is 8 molar. The concentration of product at equilibrium is 2 molar. Now you tell me, since equilibrium is established in the reaction, will the concentration of reactant change now? The concentration of reactant and product is not going to change because the moles of reactant and product are not going to change. As simple as that, right? That's why I told you, when equilibrium is established in the reaction, the moles of reactant product, they become fixed. The concentration of reactant product, they become fixed. In the similar way, the partial pressure, the pressure of reactant product, it becomes fixed as well. So, one thing which I would want you guys to analyze here. What do you think? At equilibrium, whose concentration is more? I would say concentration of reactant at equilibrium is greater than that of concentration of product at equilibrium in this particular scenario. So if you will have to represent it with the help of graph, you can do that as well. Concentration versus time. Concentration versus time. What is happening to the concentration of reactant with time? The concentration of reactant is decreasing. The concentration of product is increasing, right? The concentration of reactant is decreasing with time. The concentration of reactant is decreasing with time. So concentration of reactant decreases and attains a fixed value, does not change afterwards. Similarly, concentration of product, it increases for some time and then attains a fixed value, right? So can I say this is the time after which, the concentration of reactant as well as product has attained a fixed value. It does not change at all. So this particular time represents what? It represents equilibrium. Now you can see at equilibrium, what is the concentration of reactant? This point represents concentration of reactant at equilibrium, and this particular point, it represents concentration of product at equilibrium. Now you try to understand, is the concentration of reactant at equilibrium more or concentration of product? I would say concentration of reactant is greater than that of concentration of product at equilibrium. So this is one of the scenarios which clearly shows you the equilibrium basically. I hope this is clear to everyone. Yeah? Right, my dear students? This was one case. This was case number 1. Now looking at case number 2. Let's try to understand equilibrium a bit more in detail with case number 2. This was case number 1. Now let's have a look on case number 2. My dear students, for example, I'm again going to take the same reaction. A gives B. This is the reaction. Volume of the vessel in which reaction takes place, that's 1 liter. For example, initially at time t is equal to 0, I have got 10 moles of reactant. There will be 0 moles of product. I'm assuming that when 50% of reaction is completed, equilibrium is established in the reaction. So when 50% of reaction is completed, what does that mean? That means out of 10 moles of reactant, 50% of 10 would have got converted into product, right? So 50% of 10 means 5. So out of 10 moles of A, 5 moles of A would have got converted into product. So I'll be left with 5 moles of reactant. I had 10 moles. Out of 10, 5 moles are getting converted. So I'll be left with 5 moles of A. So if I ask you how many moles of B would have got formed, 5 moles of B would have got formed as well. Now I'm assuming that equilibrium is established when 50% reaction is completed, right? When 50% reaction is completed, I would say equilibrium is established. And my dear students, when equilibrium is established in the reaction, I would say the rate of forward and backward reaction would have got equalized, right? And if the rate of forward and backward reaction would have got equal, that means now if 1 mole of reactant will start getting converted into product, at the same time, 1 mole of product will start getting converted into reactant as well. So what will happen? Will the moles of reactant and product change now? No. The moles of reactant product, they have attained a fixed value. Right? They have attained a fixed value. Similarly, the concentration of reactant and product, they have attained a fixed value at equilibrium. Perfect. And this is one clear example at which you can say the moles of reactant and product at equilibrium, they are same. The concentration of reactant and product at equilibrium, it is same. What is the condition? The condition is the moles of reactant product, they should be constant, right? In this case, the moles of reactant, they were constant, but they were not same, right? Over here, they are constant, but at the same time, they are same as well. So that is one more case over here. So if I want you guys to represent it with the help of graph, concentration versus time. So you can say concentration of reactant decrease with time, then attains a fixed value. Concentration of product increase with time, then attains a fixed value, right? And my dear students, this is the time after which the concentration of reactant has attained a fixed value. So I would say this point represents equilibrium, right? And this is the graph which shows that the concentration of reactant and product at equilibrium is same. Yeah. So both these graphs, they do represent equilibrium. What is the condition for equilibrium? The concentration of reactant products, they should be fixed. They should be constant, right? They can be constant. They can be same as well as in this case. Over here, the concentration of reactant product was not same, but they were fixed, right? And the condition is they should be fixed. So this represents equilibrium. Perfect. Even this represents equilibrium, right? Is this clear to everyone? Let me know once in the chats. Then I'll make you understand the third case. Let me know quickly in the chats if all these things are clear till here. Then I'll be showing you the third case. The third case for equilibrium. For example, I've got a reaction like this. A gives B. I'm assuming that 80% reaction when completed, equilibrium is established. Okay. So for example, time t is equal to 0. I've got 10 moles of A in the container. This will be 0. Now at equilibrium, 80% of reactant has got converted into product. What is 80% of 10? That is 8. So out of 10 moles of reactant, 8 moles would have got converted into products. So I'll be left with 2 moles of reactants at equilibrium. And 8 moles of products would have got formed. Now I'm assuming equilibrium is established. That means the rate with which forward reaction moves, with the same rate, backward reaction moves. If 1 mole of reactant starts getting converted into product, at the same time, 1 mole of product will start getting converted into reactant. With that, the number of moles of reactant and product won't change, right? Similarly, the concentration of reactant and product won't change. Perfect. And this is the scenario in which you can see, no doubt, the concentrations have become fixed, but the concentration of reactant at equilibrium is less than that of concentration of product at equilibrium. As you can see the values, you can show it with the help of graph as well. This is, for example, concentration. This is, for example, time. And you know, concentration of reactant decrease with time, attains a fixed value. Concentration of product increase with time, attains a fixed value. This is reactant, this is product. And this is the point after which the concentration of reactant product does not change. So this is the point which represents equilibrium basically. And this graph represents that equilibrium in which the concentration of reactant is less than that of concentration of product at equilibrium. So quickly in the charts if this is clear. So my dear students, there are 3 graphs. There are 3 graphs which are correctly representing equilibrium. This is representing equilibrium. Absolutely. Even this is representing. The other one is also representing. Perfect. Right? So when you want to show equilibrium on the graph for concentration versus time, there are three graphs which represents equilibrium, and all the three graphs which I showed you. When you want to show equilibrium on rate versus time curve, there is only one graph, rate of forward backward reaction, that should become equal. So my dear students, I just want you guys to remember one thing. When you define equilibrium in terms of concentration, when you define equilibrium in terms of concentration of reactant and product, the condition is the concentration of reactant product should become constant. It can be same as well, right? But when you define equilibrium in terms of rate, the condition is the rate of forward backward reaction should be equal, should be same. Over here the term is constant, over here the term is same, equal, right? Is this clear to every single guy? Quickly in the chats. I'm going to give you one simple question over here. Tell me how many curves represent equilibrium over here. This is rate, this is time. Rate versus time. Tell me how many graphs represent equilibrium over here. This is concentration, this is time. Again, this is concentration, this is time. Again, this is rate, this is time. Tell me how many graphs correctly represent equilibrium out of the 4 graphs. I'm just waiting for your answers. From this question, I'll get to know whether you got the concept of equilibrium or not. Quickly. See, as per concentration of reactant product should become fixed. So this represents equilibrium. Concentration of reactant product should become fixed. It can be equal as well. This represents, right? As per rate of forward reaction and backward reaction should become equalized. This represents equilibrium. But over here, if you see, this point is the rate of forward reaction. This point represents rate of backward reaction. So is the rate of forward and backward reaction same? No, it's not same. So the first graph does not represent equilibrium, right? Right, people? Quickly. Is this clear to everyone? Is every single thing clear till here? Say yes or no in the chats. Say yes or no in the chats. Say yes or no in the chats. Quickly. Quickly, guys. Everyone. Yes, done and dusted? Perfect. Now, my dear students, there is one law, which is what you call as the law of mass action. This law of mass action, let me tell you, it's a complete theoretical concept. It is a complete theoretical concept. It does not have any experimental background. It does not have any experimental background. Point number 1. Point number 2, this law of mass action was given by 2 scientists. This law of mass action was given by 2 scientists, Goldberg and Lavey, right? Now the point is, what this law of mass action states. As far as its statement is concerned, as per the law of mass action is concerned, rate of reaction is directly proportional to the product of active masses of reactants raised to the powers of their stoichiometric coefficient. Now, what does that mean? Have a look what that means. For example, you have got a reaction like this. A plus B, it gives C plus D. This is one general balanced chemical equation, right? Let's say this is N1, or just a second. Let's say we have got a balanced chemical equation in this format, N1A plus N2B. For example, it gives N3C, and with this, you get N4D as well. This is a balanced chemical equation in which N1, N2, N3, N4, these are the stoichiometric coefficients of reactants and products. Now, what law of mass action states that? Law of mass action states that rate of reaction is directly proportional. Rate of reaction, the speed with which reaction moves, that's rate. Rate of reaction, that's directly proportional to the product of active masses of reactants. Reactant here is A and B. So I'll write active mass of A multiplied by active mass of B, product of active masses of reactants, raised to the powers of their stoichiometric coefficients. What is the stoichiometric coefficient of A? That's N1. So this is active mass of A raised per N1. This active mass of B raised per N2. Right? Now you must be thinking what active masses are. You'll get the idea in some time. But first, try to remember this particular statement. As per law of mass action is concerned, rate of reaction, the speed with which reaction moves, is directly proportional to the product of active masses of reactants raised to the powers of their stoichiometric coefficients. Right? Now, my dear students, before talking about the active masses in detail, let me tell you one more important thing. Try to understand what exactly I'm going to say. Try to understand what exactly I'm going to say. Have a look, people. For example, I've got a reaction like this. N1A plus N2B. I'm showing the reversible sign in the middle. It is N3C plus N4D. This is a balanced chemical equation. Now, if I ask you whether this is only one reaction or these are actually two reactions. These are actually two reactions. Forward, backward. Right? Forward, backward. Right, people? These are actually two reactions. One is forward and one is backward. Now, people, if these are two reactions, one forward, one backward, let's say this is your forward reaction. And what is my backward reaction then? The backward reaction is going to be this. N3C plus N4D, it gives N1A plus N2B. This is my forward reaction and this is my backward reaction. Now, as per law of mass action is concerned, rate of reaction. Over here, I'll write rate of forward reaction. Directly proportional to product of active masses of reactants. So active mass of A multiplied by active mass of B raised to the powers their stoichiometric coefficient. This N1, this N2. So active mass of A raised per N1, active mass of B raised per N2. Right? Similarly, rate of backward reaction. It is directly proportional to product of active masses of reactants. Here reactants are C and D. So it's going to be active mass of C raised per N3, active mass of D raised per N4. Perfect. Now, if you remove the proportionality sign, it's going to be Kf, which is a constant, active mass of A raised per N1, active mass of B raised per N2. And over here, rate of backward reaction is equal to, the constant here is Kb, this is active mass of C raised per N3, active mass of D raised per N4. Now, my dear students, just tell me one simple thing. We got two constants basically. This Rf, first of all, what do I call this? This is called as the rate of forward reaction. This is called as the rate of forward reaction. What is this Kf? This Kf is called as the rate constant. This is called as the rate constant of forward reaction. Rate constant of forward reaction. Similarly, what is this Rb? This is the rate of backward reaction. This is the rate of backward reaction. And what is this Kb over here? This is the rate constant of backward reaction. This is the rate constant for backward reaction. Now, my dear students, try to understand few things. I told you a few minutes back, when the reaction starts, the rate of forward reaction decreases and rate of backward reaction increases with time. And there comes a time when rate of forward and backward reaction becomes equal. That stage in a reaction is what we call as equilibrium. So we know at equilibrium, rate of forward and backward reaction becomes equal. If rate of forward and backward reaction becomes equal, I would say Kf multiplied by active mass of A raised per N1, active mass of B raised per N2, it becomes equal to Kb, active mass of C raised per N3 and active mass of D raised per N4. Correct till here? Absolutely correct. Now, dear students, try to understand. This Kf I'm writing as such, divided by this Kb I'm taking into the denominator. Kf divided by Kb is equal to, this is active mass of C raised per N3, active mass of D raised per N4 divided by active mass of A raised per N1 and active mass of B raised per N2. Right? What is Kf? Rate constant of forward reaction. What is Kb? Rate constant of backward reaction. So this is constant, this is constant. Division of two constants, it becomes one more constant, which is what you call as equilibrium constant. And equilibrium constant is nothing. It is represented by Keq. It is represented by Keq. As simple as that. So, my dear students, how do you represent equilibrium constant. How do you write the expression of equilibrium constant? Equilibrium constant, again I'm telling you, it's nothing. It is just the ratio of rate constant of forward reaction to that of rate constant of backward reaction. And how do you write its expression? In the numerator, these are active masses of products. Active masses of products raised by their stoichiometric coefficients. Active masses of reactants raised by their stoichiometric coefficients. This is the general way by means of which you can write the equilibrium constant of the reaction. Right? Perfect. Now let's try to analyze this a bit more in detail. Let's try to analyze this a bit more in detail. Have a look, people. What did I say? I said equilibrium constant. How do I write its expression? Active mass of C raised by N3, active mass of D raised by N4 divided by active mass of A raised by N1, active mass of B raised by N2. Right? Now, dear students, three things which I would want you guys to remember directly from now onwards. Three things, just three things. Whenever you see any reactant or product, in aqueous state, that means in the bracket, it will be mentioned as AQ. Do remember, for that particular reactant or product, which will be in aqueous state, its active mass will be taken its concentration. Similarly, my dear students, whenever you have any reactant or product in gaseous phase, its active mass can be taken its concentration or pressure. Because for gases, both the terms are defined. Concentration as well as pressure, both the terms are defined for gases. Right? Now, dear students, for any reactant or product which is in pure solid state, right? That means in the bracket it will be mentioned as S. Its active mass is taken as constant. Its active mass is a constant. And to reduce our calculation, basically, that constant is taken as 1. Similarly, whenever any reactant and product is present in pure liquid state, in the bracket it's mentioned as L. So generally, its active mass will be also taken as constant, which will be taken as unity. Right? These are the four things which I would want every one of you to remember. Any reactant product in aqueous state, its active mass is concentration. Gaseous state, its active mass can be concentration as well as pressure. Solid liquid, unity, directly. Now, based on all this, based on active mass, I'm going to classify equilibrium constant into many types. One is 1 KEQ. One equilibrium constant is called as KC, one is called as KP, and one more equilibrium constant is called as KX. There is one more, that is KPC, which we do not need here. That's something which we need in electrochemistry, not here, right? So first of all, what is this KC, what is this KP, and what is KX? In the expression of equilibrium constant, what do we have? We have got active masses. So whenever in place of active masses, you use the term concentration. Whenever in place of active masses, you use the term concentration. For example, you write concentration of C raised power N3, concentration of D raised power N4, etc. Like this. At that point of time, your KEQ becomes KC. So your KEQ becomes KC. So if I want you guys to write the KC expression, how you are going to write it? It's going to be concentration of C at equilibrium raised by N3, concentration of D at equilibrium raised by N4 divided by concentration of A at equilibrium raised by N1, concentration of B at equilibrium raised by N2. All these concentrations of reactants and products, they are measured at equilibrium, right? Now, what is KP? My dear students, if for example, in place of active masses, you use the term pressure, then KEQ is what I'll be calling as KP. And KP expression, how will I be writing it? It's going to be partial pressure of C at equilibrium raised by N3, partial pressure of D at equilibrium raised by N4, partial pressure of A at equilibrium raised by N1, partial pressure of B at equilibrium raised by N2. Right? Now you must be thinking what these partial pressures are. You'll get the idea in some time. If you want to write the expression for Kx, so what do you need to do? Replace active masses by the term mole fraction. So it's going to be mole fraction of C at equilibrium raised by N3, mole fraction of D at equilibrium raised by N4, mole fraction of A at equilibrium raised by N1, mole fraction of B at equilibrium raised by N2. So this is how you write the expressions of Kp, Kc and Kx. Right? Say yes or no in the chat if this point is clear to everyone. If this point is clear to everyone quickly. Yeah? Say yes or no quickly with the thumbs ups in the chats. Then only I can move ahead. Then only, my dear students, I can move ahead. Till now, I've not done any questions because this is all basics going on right now. Perfectly done? Yeah? Perfectly done? Okay, this partial pressure, I'll let you know in some time what it means. Okay, when I'll be teaching you KP-KC relation, then I'll make you understand what this partial pressure is. Or if you have studied states of matter from me, I've done states of matter already, right? There we have discussed Dalton's law of partial pressure. In Dalton's law of partial pressure, you would have studied it, right? When will you come to Tamil Nadu? Tamil Nadu, I'll be coming soon, maybe next week or after that. Just be ready to meet. Yeah. All right, people. So let's move on now. Let's move on and talk about few interesting things. All right. These are two reactions which I've taken over here. Will we be able to write their KP-KC expressions? We should be able to write their KP-KC expression, right? My dear students, if I write the KC expression, then I should use the term concentration. I'll start with the product. It's going to be concentration of HI at equilibrium raised by stoichiometric coefficient divided by concentration of H2 at equilibrium raised by stoichiometric coefficient, concentration of I2 at equilibrium raised by stoichiometric coefficient. Similarly, if you want to write the expression for Kp, for gases, concentration as well as pressure is defined. So you can write Kc expression as well as Kp expression. Kp expression is going to be partial pressure of H2 at equilibrium, partial pressure of Hi at equilibrium raised by stoichiometric coefficient divided by partial pressure of H2 at equilibrium raised by stoichiometric coefficient, partial pressure of I2 at equilibrium raised by stoichiometric coefficient, right? Similarly, my dear students, if I ask you to calculate delta Ng for the reaction, can you calculate delta Ng for this reaction? What is delta Ng? If you remember, number of moles of gaseous products minus number of moles of gaseous reactants. So first of all, in order to calculate delta Ng, what do we need? We need number of moles of gaseous products and number of moles of gaseous reactants. So how many moles of gaseous products we have? We have got 2 moles of gaseous products minus. How many moles of gaseous reactants we have? We have got 1 plus 1, 2 moles of gaseous reactants. So delta Ng for this reaction will definitely come out to be 0. Simple. Look at the next reaction. All the reactants products, they are present in gaseous state. They are present in gaseous state, right? Try to write Kc expression. Start from the product. It is concentration of PCl3 at equilibrium raised by stoichiometric coefficient, concentration of Cl2 at equilibrium raised by stoichiometric coefficient divided by concentration of PCl5 at equilibrium raised by stoichiometric coefficient, right? Similarly, for gases, you know concentration as well as pressure is defined. Now write the Kp expression. Write the Kp expression. Start with the product. It's going to be partial pressure of PCl3 at equilibrium raised by 1, partial pressure of Cl2 at equilibrium raised by 1 divided by partial pressure of PCl5 at equilibrium raised by 1. This is how you write Kp expression for this particular reaction, right? And my dear students, if I ask you to calculate delta Ng for this reaction, it's going to be number of moles of gaseous products. These are your gaseous products. So 1 plus 1 makes it 2 minus number of moles of gaseous reactant, which is 1. So 2 minus 1 will make it 1 only. So delta Ng for this particular reaction is 1 over here, right? Perfect. Is this clear to everyone? Is this clear to everyone? Now, dear students, have a look over here. This is, so by the way, these reactions which I took over here, these were homogeneous gaseous phase reactions. All the reactants and products were in gaseous state. So it was the homogeneous gaseous phase reaction. Now, all the reactants and products, they are not in gaseous state. They are not in gaseous state. It is just one product is in gaseous state. So this is something which I'll be calling as heterogeneous gaseous phase reaction, right? Heterogeneous gaseous reaction. Similarly, this is solid, this is gas, this is gas. All are not gas. If all were in gaseous phase, they're homogeneous. But all are not, so it's heterogeneous. Now try to understand. First of all, write the expression for Kc. Kc expression. Start with the product. This is solid, its ectomass is 1. This is gas, its concentration of carbon dioxide at equilibrium raised by stoichiometric coefficient divided by reactant is in solid state, its ectomass is 1. Nothing to do with that. Write the Kp expression. Kp expression. Again, it's just going to be partial pressure of carbon dioxide at equilibrium raised by stoichiometric coefficient. That's all. Calculate delta Ng for the reaction. Delta Ng for the reaction. Number of moles of gaseous products, which is 1 minus number of moles of gaseous reactants. These are in solid, nothing to do with them. So 1 is basically the delta Ng for the reaction, right? What happened to this? Okay, so I hope this is clear. Now talking about other one. This is solid, this is gas, this is gas. Write the Kc expression first of all. So solid, I've got nothing to do with solid, its active mass is 1. So Kc, concentration of SO3 at equilibrium raised per stoichiometric coefficient divided by its concentration of O2 at equilibrium raised per stoichiometric coefficient. I've got nothing to do with solid. What about the Kp expression? Again, start with the product. It's partial pressure of SO3 at equilibrium raised per 1 divided by it's going to be partial pressure of O2 at equilibrium raised per 3 by 2. This is how you guys are going to write Kp expression as well. Now, if you got Kp and Kc expression, then easily you can calculate delta Ng for this reaction. Number of moles of gaseous product, which is 1, minus number of moles of gaseous reactant, which is 3 by 2. So 1 minus 3 by 2 makes it minus 1 by 2. So this is delta Ng for the reaction. So I hope you got to know how to write Kp expression, how to write Kc expression, how to get the delta Ng, right? Perfect, guys? Perfect? Perfect? I'm sure these things you can easily do now. I'm sure these things you can easily do. You can write Kp Kc expression for this. You can write Kp Kc expression for this as well. You can calculate delta Ng for this reaction, delta Ng for this reaction, right? You should be in a position to write that. Okay? Or let me write one example. Kc for this particular reaction. Concentration of NO2 at equilibrium raised per 2 divided by concentration of N2O4 at equilibrium raised per 1. What about Kp? Kp is going to be partial pressure of NO2 at equilibrium raised per 2 divided by partial pressure of N2O4 at equilibrium raised per 1. Perfect. Delta Ng for this reaction, if you want to calculate, it's number of moles of gaseous product, which is 2, minus number of moles of gaseous reactant, which is 1. The value of delta Ng comes out to be 1 only. Correct? Now, similarly, the next one. Write the Kc expression. Kc is going to be concentration of NH3 at equilibrium raised per 1, concentration of H2S at equilibrium raised per 1 divided by, this is solid, its active mass is unity, nothing to do with that. Similarly, Kp expression. Partial pressure of NH3 at equilibrium raised per 1, partial pressure of H2S at equilibrium raised per 1. This is solid, its active mass is unity. If I ask you, what about the delta Ng for this reaction? Number of moles of gaseous products. This is 1 plus 1, that's 2, minus number of moles of gaseous reactant. This is solid, so nothing to do with that, right? So it's 2 only. So 2 is going to be the delta Ng for the reaction. I hope you can easily do it, right? Perfect. Harish, you can check the live session. I have taken a video in which I have given the test planner. Just go to the lives category. You'll find at the bottom, you'll find like last week, I've taken a session in which I've given the whole test plan. Just watch it. Perfect. Where are you? Even we have made one Telegram channel as well for the test series students. I don't know where are you basically, right? So then you'll keep on commenting, where is the schedule? I have given the already schedule like 2 times on my Telegram everywhere. I've made a separate Telegram group for the test series students. So you should be active basically. It's your loss. It's not my loss. All right. So I hope till now, every single thing is clear. Now, my dear students, now comes something interesting. Over here, I'm going to write relation between Kp and Kc. This is something important. A relation between Kp and Kc. A relation between Kp and Kc. This is important, okay? Try to understand what exactly I'm going to do. For example, I'm going to make a reaction. N1A, for example, N1A gas, it gives N2B gas. This is one very simple reaction. N1A gas gives N2B gas. First of all, if I ask you, what about the delta Ng for this reaction? Delta Ng for this reaction is number of moles of gaseous products minus number of moles of gaseous reactant. So N2 minus N1. N2 minus N1, it is the delta Ng for the reaction. N2 minus N1, it is a delta Ng for the reaction. Now, dear students, if I ask you to write the Kc expression is going to be concentration of B at equilibrium raised to the power N2 divided by concentration of A at equilibrium raised to the power N1. If I ask you to write Kp expression, it's going to be partial pressure of B at equilibrium raised to the power N2 divided by partial pressure of A at equilibrium raised to the power N1. Now, first of all, before doing any sort of calculation here, let me ask you what these partial pressure of A and B are. See guys, it's simple. At time t is equal to 0, there will be only a reactant in the container, right? At time t is equal to 0, when the reaction has not started, there will be only gas A in the container, right? Now, when the reaction will start, that means moles of reactant will keep on decreasing. Moles of product will keep on increasing. Can I say at one point of time, equilibrium will be established, at which rate of forward and backward reaction becomes equal? So if I ask you at equilibrium, how many gases will be there in the container? Will there be only gas A or gas B also in the container at equilibrium? Can you let me know in the chats? I would say at equilibrium, there will be two gases in the container. Gas A, some moles of gas A left in the container, and some moles of gas B which would have got formed. So at equilibrium, there will be two gases in the container. So can I say at equilibrium, there will be a gaseous mixture? At equilibrium, there will be a gaseous mixture, right? Perfect. In that gaseous mixture, how many gases are there? Two gases. So I would say at equilibrium, there will be a gaseous mixture present in the container. This gaseous mixture, it contains the moles of gas A left in the container, similarly the moles of gas B which would have formed. So this is the mixture of gases which is present at equilibrium. Let me assume that the total pressure of this particular gaseous mixture is PT. PT represents the total pressure of the mixture at equilibrium. Now, the total pressure of the mixture at equilibrium will be due to PA as well as PB. What is PA? PA is basically the contribution made by gas A towards the total pressure of the mixture. Similarly, PB, it is the contribution made by gas B towards the total pressure of the mixture. Contribution made by A towards the total pressure, that's something which you call as partial pressure of A. Contribution made by gas B towards the total pressure of the mixture, that's called as partial pressure of B. I hope you got to know what this partial pressure is, right? So basically at equilibrium, you'll find a mixture of gas, right? There will be some moles of A left in the container, some moles of B which would have got formed. Perfect. So there is a mixture of gases in the container, right? Contribution made by gas A towards the total pressure, that's partial pressure of A at equilibrium. Contribution made by gas B towards the total pressure of the mixture, that's partial pressure of B at equilibrium. As simple as that. Now guys, what exactly I'm going to tell you right here. Try to understand what exactly I'm going to tell you. Have a look. We know as far as ideal gas equation is concerned, P is equal to nRT divided by V. Yes, every one of you will be knowing as far as the ideal gas equation is concerned. So can I say P is equal to, what is N by V? Number of moles per unit volume. Should I be calling it a concentration? So concentration multiplied by R multiplied by T. Absolutely. So if I say partial pressure of A will be equal to concentration of A multiplied by R multiplied by T. If I say pressure of B, it's going to be concentration of B multiplied by R multiplied by T. Absolutely, right? Now look at this particular scenario. Kp is equal to partial pressure of B at equilibrium. Can I write concentration of B at equilibrium multiplied by R multiplied by T whole raised by what? Whole raised by N2, right? Divided by partial pressure of A at equilibrium. Partial pressure of A at equilibrium will be equal to concentration of A at equilibrium multiplied by R multiplied by T whole raised by N1. Correct? Right, people? So can I write the whole scenario like this? Concentration of B at equilibrium raised by N2 divided by concentration of A at equilibrium raised by N1. This is RT, this is RT. RT raised by N2, RT raised by N1. So this has to be RT raised to the power RT raised by N2 minus N1. And what is N2 minus N1? N2 minus N1 is nothing, that's delta Ng for the reaction. If I ask you what about this whole term? This whole term over here, which you can check, it is basically Kc. So it is Kc multiplied by RT raised to the power what? Raised to the power delta Ng. So basically we got one direct result which you guys are going to remember from now onwards. For a gaseous phase reaction, Kp is equal to Kc RT raised to the power delta N, right? So this is the first and the important result which you guys are going to remember from now on. Kp is equal to Kc. This particular reaction, this particular equation, it is used many a times. For example, Kp of the reaction will be given and you are supposed to calculate Kc. You can use this equation. Kc of the reaction is given. You are supposed to calculate its Kp. You can use this particular result as well to do the same. Yeah. So dear students, we got one very, very, very important result. And let's try to utilize this particular result in a proper format. Have a look. I told you Kp is equal to Kc RT raised by delta Ng. This is the reaction, this is the relation between Kp and Kc. Now, what all things we can generalize from here? See guys, what is this R? R is basically the gas constant, right? Do you remember its value? It's one of the values 0.0821 atm liter per Kelvin per mole. In order to reduce the calculation, this 0.0821 is written as 1 by 12, right? 0.0821 is written as 1 by 12 to reduce the calculation. Now, my dear students, try to understand. T stands for the temperature at which the reaction takes place. Now, the case number 1. If, for example, the reaction is taking place at 12 Kelvin temperature. If the temperature of the reaction is 12 Kelvin. If the reaction is proceeding at 12 Kelvin. If the reaction is proceeding at 12 Kelvin, tell me what will be the value of R into T. What will be the value of R into T? R is 1 by 12. Temperature is 12. 12 cancel. RT value is 1, right? If RT value is 1, 1 raised per anything is 1. That means any such reaction which is carried out at 12 Kelvin temperature, or that particular reaction, Kp will be always equal to Kc. This is case number 1. This is your case number 1. Case number 2. If for example, the temperature at which the reaction proceeds is greater than 12 Kelvin. If temperature is greater than 12 Kelvin, what will happen to the RT value? R is 1 by 12 and T is greater than 12. So R multiplied by T will be greater than 1. R multiplied by T is greater than 1. Now over here, 3 cases arise. First case, if delta Ng of such reaction is 0, if delta Ng is 0, so anything raised by 0 is 1. So I would say at that point of time, Kp will be equal to Kc. Now second case in the same. If for example, delta Ng for the reaction is greater than 0. If delta Ng for the reaction is greater than 0, this term is already greater than 1. This term is greater than 0. So what can we conclude? We can conclude Kp value will be greater than Kc. Similarly, the third case which arises here, if for example, delta Ng value is less than 0, at that point of time, you can categorically say Kp value is less than Kc, right? Simple. Perfect. Similarly, case number 3. What is case number 3? Case number 3 is if temperature of the reaction is less than 12 Kelvin. If the reaction is carried out at less than 12 Kelvin. If temperature is less than 12 Kelvin, R multiplied by T. R is 1 by 12, temperature is less than. It's going to be less than 1. If RT is less than 1, then over here case 1 arises. First case, if delta Ng for the reaction is 0. This term right now is less than 1. Less than 1 raised power 0 is 1 only. Therefore, Kp value has to be equal to Kc. First point. Second point. If delta Ng over here for the reaction is greater than 0, and in this particular case, Kp will be less than Kc. And the third one, if delta Ng for the reaction is less than 0, you would say Kp will be greater than Kc, right? So it depends on the temperature at which the reaction proceeds. Accordingly, you can say whether Kp will be greater than Kc or less than Kc or equal to Kc, depending on the temperature at which the reaction proceeds. Perfect. Now, my dear students, there is one more thing. Let's try to understand that as well. There is one more thing. See, I give you a result. The result is Kp is equal to Kc RT raised to the power delta Ng for a gaseous phase reaction, right? Now, if we use some mathematics over here, if I multiply throughout by log, it becomes log of Kp is equal to log of Kc RT raised by delta Ng. Now, my dear students, you can write it as log of Kp is equal to log of m into n is equal to log of m plus log of n plus log of n. Or finally, you can write it like this. Log of Kp is equal to, it's going to be log of Kc plus log of m raised power n is L log n. So delta ng comes to the front. Then you would be writing log of Rt. Perfect. This is the logarithmic form of the same equation. This is the logarithmic form of same equation. And as far as this particular equation is concerned, you can plot a curve. You can plot a graph. The graph is going to be between log of Kp versus what? Log of Kp versus log of Rt. My dear students, you have to plot a graph between log of Kp, which you are plotting along y-axis, log of Rt, which you are plotting along x-axis. This delta ng has to be m. The sign over here is positive. This log of Kc is your intercept. So y is equal to mx plus c. Y is equal to mx plus c. It's absolutely going to be a straight line like this. What about the slope of this graph? The slope means m value, and m right here is equal to delta ng. What about the intercept? Intercept means the c value, and c value when you compare, it comes out to be log of Kc. So this intercept is nothing, it's log of Kc over here. So this is one graph which might be asked. Anything can be asked out of this, right? You'll begin with the graph, you'll begin with the slope, and you will have to identify what is the delta ng for the reaction. You can easily do that. Yeah? Perfect. So right now, what did we do? We saw the relation between Kp and Kc. Perfect. There is one more relation. What is that going to be? There is one more relation. Let's try to understand that as well. One more relation is between Kp and Kx. Let's see what exactly is the relation between Kp and Kx. Try to understand this one as well. This is again important and simple at the same time. For example, you have got the reaction like this. N1A gas in equilibrium with, for example, N2B gas. This is the reaction which we have. First of all, I want you guys to write its expression for Kp. Okay, before writing expression for Kp, can you let me know what is the delta ng for the reaction? Number of moles of gaseous product, which is N2, minus number of moles of gaseous reactant, which is N1. Correct? So delta ng you calculated. Now at the same time, Kp has to be equal to partial pressure of B at equilibrium raised by N2 divided by partial pressure of A at equilibrium raised by N1. Similarly, I am asking you, what is the expression for Kx? Kx is just going to be mole fraction of B at equilibrium raised by N2 divided by mole fraction of A at equilibrium raised to the power N1. Correct? Yes? Now, my dear students, you tell me one thing. When equilibrium will be established in the reaction, at equilibrium, there will be some moles of A in the container. There will be some moles of B in the container as well. So at equilibrium, will there be only one gas or two gases in the container? So at equilibrium, there will be gas A as well as gas B in the container. Few moles of gas A which are left and few moles of gas B which have got formed. So at equilibrium, there is a gaseous mixture present in the container. At equilibrium, there is a gaseous mixture present in the container. Now, the total pressure of the gaseous mixture at equilibrium, I'm representing it with PTEQ. This is the total pressure of the mixture. And the total pressure of the mixture will be equal to the sum of their partial pressures. So, partial pressure of A partial pressure of A at equilibrium plus partial pressure of B at equilibrium. Perfect. This will be equal to total pressure of the mixture. Now, you must be studied partial pressure of A at equilibrium will be equal to total pressure of the mixture at equilibrium multiplied by mole fraction of A at equilibrium. Similarly, partial pressure of B. How do we calculate partial pressure of gas? It's total pressure of the mixture at equilibrium multiplied by mole fraction of B at equilibrium. As simple as that, right? This is something which you know because we have discussed this in states of matter as well when I taught you the Dalton's law of partial pressure. Now, my dear students, try to understand what I'm going to say. Kp has to be equal. What is partial pressure of B at equilibrium? Partial pressure of B at equilibrium can be written as total pressure of the mixture at equilibrium multiplied what? Mole fraction of B at equilibrium, right? Whole raised by what? Whole raised by N2 divided by partial pressure of A at equilibrium. It's going to be total pressure of mixture at equilibrium raised by total pressure of mixture at equilibrium multiplied by just a second, guys. This was B, okay, this A. So it's mole fraction of A at equilibrium. And whole raised per what? Whole raised per N1. Let's try to understand what do we get over here. Let's try to understand what do we get over here. My dear students, you can write it like this. PT raised per N2, PT raised per N1. So is it going to be total pressure of the mixture at equilibrium raised per N2 minus N1? N2 minus N1 is delta Ng. Over here you got mole fraction of B at equilibrium raised per N2, mole fraction of A at equilibrium raised per N1. So mole fraction of B at equilibrium raised per N2 divided by mole fraction of A at equilibrium raised per N1, that basically denotes your Kx. So right here, you got one more amazing result. And what is this result? The result is very simple. Kp is equal to Kx multiplied by total pressure of the mixture at equilibrium raised per what? Raised per what? Raised per delta Ng. This is one result which connects your Kp with Kx. Right? This one result which connects your Kp and Kx. So finally, what did we get to know? Finally, what did we get to know? We got to know your Kp is equal to, we got to know your Kp is equal to Kx multiplied by total pressure of the mixture at equilibrium raised to the power delta Ng. This is the result which we got. This is the relation between your Kp and Kx. Now at the same time, if you want to convert it into the logarithmic form, so multiply throughout by log, it is going to be log of Kp has to be equal to log of Kx as such. This is total pressure at equilibrium raised to the power delta Ng. Now use a bit of maths here. So log of Kp has to be equal to log of m into n, which has to be equal to log of m plus log of n plus log of n. Now you can convert it like this. So log of Kp is equal to, it's log of Kx plus log of m raised per n, which is n log m. So delta Ng comes to the front, right? It's going to be log of total pressure of the mixture at equilibrium. That's all. So this is the logarithmic form of the same equation. This is the logarithmic form of the same equation. Now, if you got the logarithmic form of the same equation, you can directly make one curve, and the curve has to be between log of Kp versus log of total pressure of the mixture at equilibrium. Now, can you let me know what will be the nature of this curve? Can you let me know what is the nature of this curve? My dear students, log Kp, you are plotting along y-axis. Log of Pt, you are plotting along x-axis. So this has to be your m, and this has to be c. Y is equal to mx plus c. Isn't it again going to be a straight line? Absolutely, it's a straight line. What about the slope of this graph? Slope is basically m, and m value comes out to be delta Ng. And my dear students, what about this intercept? Intercept is c, and c value, after getting, we it as log of Kx. Perfect. Perfect. So till now, we got two results. Till now, we got two results. The first result was Kp is equal to Kc RT raised power delta Ng for the gaseous phase reaction. The second result is Kp is equal to Kx multiplied by total pressure of the mixture at equilibrium raised power delta Ng. Now look at the two equations, my dear students. Kp is equal to this, Kp is equal to this. From equation 1 and equation 2, can't we say Kc multiplied by RT raised power delta Ng has to be equal to Kx multiplied by Pt at equilibrium raised power delta Ng? Correct? So I can say Kc is equal to Kx. This is total pressure of the mixture at equilibrium divided by RT whole raised power what? Whole raised power delta Ng. This is the final relation, and this is the relation which connects your Kc with Kx. So I hope all these things are absolutely clear, right? Is it clear, guys? Is it clear? Is it clear? Let me know once in the chats quickly if every single thing is clear till here. Yeah? Right? So I think everything is sorted. So Kc is equal to Kx. This is Pt divided by RT raised by delta Ng. Right. Okay, if I ask you one thing, if we multiply this equation throughout by log, after doing every calculation, the final result will be like this. Log of kc is equal to log of kx plus delta ng log of pt divided by rt. This will be the final expression. After multiplying with a log, this will be the final expression. So at the end, if I ask you to draw a graph, to plot a graph between log of kc and log of pt divided by rt, can you let me know what will be the nature of this curve? Can you let me know what will be the nature of this curve? Log of kc you are plotting along y-axis. Log of pt divided by rt you are plotting along x-axis. So this has to be your m, right? And this has to be your c. Y is equal to mx plus c. Y is equal to mx plus c is going to be something like this. Slope of this graph is delta ng, right? What about the intercept? Intercept is going to be log of kx. So this is something which every one of you must know. Okay, perfect. So my dear students, one very simple question. What very simple question? Write the Kp expression in the form of Kc. You have to write Kp in terms of Kc basically. So for the reaction number one, what is delta Ng? Delta Ng is number of moles of gaseous product, which is 2, minus number of moles of gaseous reactant, which is 1 plus 1, that's 2. So 2 minus 2 is 0. So we know Kp is nothing, that is Kc. RT raised by delta Ng is 0. So for the first reaction, I must say Kp is equal to Kc. Simple. For the first reaction, Kp is equal to Kc. Second reaction. Calculate delta Ng. Delta Ng will be equal to number of moles of gaseous products, which is 1 plus 1, 2, minus number of moles of gaseous reactant. So the value comes out to be 1. So delta Ng is 1. If delta Ng is 1, you can say Kp is equal to Kc RT raised by delta Ng. Since delta Ng is 1, so you got to know Kp is equal to Kc raised by RT. And Kp is equal to Kc RT. Right? Similarly, look at the third equation. Calculate delta Ng. Delta Ng for the reaction is equal to number of moles of gaseous products, which is 2, minus number of moles of gaseous reactants, which is 1 plus 3, that's 4. The value comes out to be minus 2. So I would say Kp is nothing, that is Kc RT raised to the power delta Ng, which is minus 2. So this is the relation between Kp and Kc. And at the end, for the fourth reaction, calculate delta Ng. Delta Ng is equal to number of moles of gaseous products, which is 1, minus number of moles of gaseous reactant, that's 0. So the value comes out to be 1. If delta Ng is 1, you can say Kp is equal to Kc RT raised by 1. So this is the relation between your Kp and Kc for the last reaction as well. Yeah? Perfect. I hope you can do these basic questions, basic things from now onwards. Easily you can do that. Now guys, there is something called as units of Kp and Kc. What are going to be the units of Kp and Kc? Right? It's again simple. For example, you have got a gaseous phase reaction. N1A gas, it's in equilibrium with N2B gas. It's a gaseous phase reaction. If I write the expression for Kc, it's going to be concentration of B at equilibrium raised by N2, concentration of A at equilibrium raised by N1. Similarly, if I ask you about the Kp expression, it's going to be Kp is going to be partial pressure of B at equilibrium raised to the power N2 divided by partial pressure of A at equilibrium raised to the power N1. Correct? Now, what about the units of Kc? This is concentration, which is moles per unit volume. Concentration moles per unit volume. So in the numerator, you have got moles liter inverse raised by N2. In the denominator, you have again got moles liter inverse raised by N1. So you can say Kc units are going to be moles liter inverse raised by N2 minus N1. So you can say Kc units are going to be moles liter inverse. N2 minus N1 is basically delta Ng for the reaction. So it's going to be delta N over here. Perfect. Right? So these are the units of your Kc. Similarly, Kp units, if you ask me. So in the numerator, there is pressure. In the denominator, there is pressure as well. Let's assume we are taking pressure in atm. So it's atm raised by N2, atm raised by N1. So it's going to be atm raised by N2 minus N1, which is basically delta N for the reaction. Perfect. So this is how you can check the units of Kp and Kc for any sort of reaction which is given to us. I hope all these things are absolutely clear to you. So say yes or no in the chats if all the things are absolutely clear. Yeah. I hope all the things are absolutely clear till here, right? Right, people? Now, moving on to characteristics of equilibrium constant. Moving on to characteristics of equilibrium constant. When you write the expression of equilibrium constant, Kc, for example, what do we need? We need concentration of reactants and products at equilibrium, right? We write concentration of product at equilibrium raised by stoichiometric coefficient divided by concentration of reactant at equilibrium raised by stoichiometric coefficient. That's what we do. So what do we need? We need the concentrations of reactants and products at equilibrium. Do we need the concentration of reactant initially? While writing the equilibrium constant expression Kc, do we need the initial concentration of reactants? No. What do we need? We need the concentration of reactants and products at equilibrium, not initial ones. So do remember, equilibrium constant, it does not depend upon initial concentration of reactants. Point number one. It does not depend upon the initial concentration of reactants. Now point number two. Equilibrium constant, it does not depend upon the catalyst as well. What the positive catalyst does? Positive catalyst, it speeds up the reaction. It speeds up the forward as well as backward reaction, due to which equilibrium is established earlier in the reaction, nothing else. But the equilibrium concentrations, they are same, right? In presence of positive catalyst, what does the positive catalyst do? Positive catalyst, it speeds up the reaction. It speeds up the forward and backward reaction. When the rate of forward and backward reaction increases, so I must say equilibrium in presence of positive catalyst is attained earlier in the reaction, nothing else, right? So in absence of catalyst, imagine that equilibrium was getting established in 1 hour. In presence of positive catalyst, same equilibrium, for example, in the reaction is being established in 10 seconds. So it just speeds up the forward backward reactions, due to which equilibrium comes in the reaction early. But the equilibrium concentrations in presence of catalyst or in absence of catalyst, it will remain the same only. If nothing happens to the equilibrium concentrations of reactants and products, that means nothing is going to happen to the value of equilibrium constant. So equilibrium constant, its value does not change in presence or absence of catalyst, whatever. Yeah. Equilibrium constant, it depends on temperature. Now you must be thinking how, right? That's something which we have to discuss afterwards. Perfect. So keep it as such. Keep it as such. I'm just telling you, equilibrium constant, it depends on the temperature. So we will have to discuss in detail how equilibrium constant changes on changing the temperature for endothermic reactions, same for exothermic reactions. That's something which is a good debate, but afterwards, not now. Okay. Equilibrium constant, it depends on the stoichiometric representation of a reaction. Stoichiometric representation of a reaction. What does that mean? For example, I've got the reaction like this. A gives B. Perfect. I'm writing its expression for Kc. Kc expression is concentration of B raised per N, concentration of B raised per stoichiometric coefficient 1 at equilibrium divided by concentration of A at equilibrium raised per 1. Correct? Right? Now, for example, if I multiply the same reaction with 2, now Kc expression will be concentration of B at equilibrium raised per 2 divided by concentration of Ba at equilibrium raised per 2 as well. So what has happened? On changing the stoichiometric representation, the value of equilibrium constant changed over here. So Kc value is coming out to be concentration of B at equilibrium raised per 1. Here it's 2, right? Perfect. Right, people? Now, the actual 3 things which you need to know about equilibrium constant, which are very important, from which questions can be easily asked. What is that? Look at the statement. When the reaction is reversed, its equilibrium constant gets inversed. What does that mean? For example, you have got the reaction like this. A gives B. This is the general reaction, whose equilibrium constant, for example, is K. Now, my dear students, when you reverse this reaction, when you reverse the same reaction, on reversing the reaction, equilibrium constant is inversed. Now, I would say the equilibrium constant of this particular reaction, it won't be K, it will be 1 by K. So the first point which you will be remembering directly from now on, right? On reversing the reaction, equilibrium constant is inversed. Point number 1. Point number 2. If the reaction is multiplied by any number, that number goes to the power of equilibrium constant. What does that mean? Over here, we have got a general reaction. A gives B, whose equilibrium constant, for example, is K. Now, for example, I'm multiplying this reaction by a number X. I'm multiplying this reaction by a number X. When you multiply the reaction by any number, that number goes to the power of equilibrium constant. Now, its equilibrium constant is going to be K raised per X, right? If you are multiplying by 2, it's K square. If you are multiplying by 3, it's K cube. If you are multiplying by 1 by 2, it's K raised per 1 by 2. Nothing else. Okay? If two reactions are added together, the equilibrium constant gets multiplied. For example, you have got the reaction like this. A plus B in equilibrium with C, its equilibrium constant is K1. Now, D plus E, it's in equilibrium with F. Let's say its equilibrium constant is K2. Now, for example, if I add these two reactions, after adding the reactions, the net reaction is going to be A plus B plus D plus C. It gives what? It gives E plus F. My dear students, it gives C plus F. Okay, so on adding the reactions, what happens to the equilibrium constants? I would say equilibrium constant of this reaction will be K1 multiplied by K2. So basically, these are three basic things which, if you remember, you can easily solve all the equations, my dear students, right? Which are based on characteristics. So point number one, which you have to remember. What is that? Number one, when a reaction is multiplied by some number, that number goes to the power of its equilibrium constant. Point number one. Point number two, if a reaction is reversed, its equilibrium constant is inversed. Point number two. Point number three, when you add two reactions, right, which are in equilibrium, the equilibrium constants are multiplied, right? Perfect? Perfect, guys? So these are some basic things which I would want all of you to remember for now. Okay?